Welcome to qnawire.
All right, so this is a fun little calculus problem that involves coupling between the x and y directions. So they tell us the forces as a function of time for each of these. And then one thing they'll add on, maybe in green, is that the y coordinate is itself a function of time. So we cannot immediately integrate this first equation because we don't know what it is. And let's go ahead and add some curly braces to indicate that those go together. So one thing that we can immediately find, since we know what the mass is the accelerations as a function of time. And we just do that by applying Newton's second law. Just divide the force by mass, basically. So do that twice to find the acceleration in the y direction. So since we start off with accelerations and we ultimately want to find positions, well, both position and velocity, but positions, we will need to integrate in order to find those. Let's go ahead and do that. Starting off with the y direction, because we need that first in order to then solve for the x direction. So you find velocity in the y direction by integrating acceleration in the y direction with respect to time. Integrate from 0 to t. What is this? We have it right over there. That's k3 over m. And then I'll use a little prime subscript since we already have t's in the limit of integration. And then we get k3 over 2m t squared. Excellent. Do that one more time in order to solve for that coveted y as function of t. Same procedure, we're just integrating velocity with respect to time. Plug in the value we just found, which is k3 over 2m t prime squared dt. And that's going to be equal to k3 over now 6m t cubed. Excellent. So now we're going to do this two more times for vx and then x respectively. So it's the same procedure, but it will look a little bit more complicated because we do have that coupling. So it's going to be the integral of acceleration. Good, good, good. But what acceleration is k1 over m plus k2 over m multiplied by what we just found, which was k3 over 6m t cubed, whole thing integrated over dt. Sorry, that should have a prime. So what this will come out to be is k1 over m, a single t over here, added to k2, k3 over 24 m squared t to the fourth power. Good, good, good. We're going to do that one more time in order to find the coordinate x. All right, so integrate velocity in the x direction over time. That will give us our limits of integration. So we have k1 over mt plus k2, k3 over 24m squared t to the fourth t prime to the fourth power. All right, and we need to start a new line because that's just not going to fit. That will give us k1 over 2m t squared plus k2, k3 over 120 m squared t to the whopping fifth power. So now we can go ahead and record this position vector by combining the x and y components. So we just said that this is k1 over 2m t squared plus k2, k3, 120 m squared t to the fifth power. This is in the I hat direction. Add that to the y component, which we said is k3 over 6m t cubed. This is in the j hat direction. That sums up what the position vector looks like. Big box. And then the velocity vector is also going to be really big. Let's do it over here. Velocity as a function of time. Next component of velocity we said was k1 over m t plus k2 k3 over 24 m squared t to the fourth power. This is in the I hat direction. And then add that to the y component, which is k3 over 2m t squared in the j hat direction, is what the velocity is.